Mhm. Oh, all right. Okay. Hello, everyone. My name is Maria Paprskarova, and I'm a PhD student of Juraj Toth. And today I would like to talk to you about our approach to modeling the behavior of meteoroids. So, what we are trying to do is to infer the physical characteristics of meteoroids. Thanks to AMOS cameras, we have a lot of visual observations to use and also a lot of multi-station observations. So we have calculations of trajectory and also the absolute brightness. So what we focus on is to build a model that would be able to fit those observations, and the parameters that we use will be our estimation of the parameters of the meteoroid. Um, in this presentation, I will focus mainly on the light curves because they very easily represent the processes that we focus on in our model, namely fragmentation and ablation. So first, some approaches to simulation that we could use. The basic building block of all our simulations are the single body simulations. Tomáš Boros already mentioned it in his presentation. It's basically simplified version of a meteoroid that doesn't fragment. It's spherical and homogeneous, so it ablates uniformly. And as a result, its light curve is this smooth, slowly increasing with a late peak and then pretty fast decrease at the end. Well, this is not how meteors typically look, so we need to build upon this model. And what we do in our approach is mostly include gross fragmentation, which means that at some points that we decide manually, we generate fragments, and those are treated as another single bodies. And in the end, their luminosity is summed up, and a resulting light curve looks something like this. So we have flares, which their shape depends on the properties of the fragments, their amount, and so on. There is also an example of this. This is a very simple one. We can generate fragments that are of any size and amount. It can be in some mass distribution or just very simply a lot of identical ones. That's good for the simulation because it doesn't have to run too many times. So we have a meteor that very clearly has some flares along the way. We look at the light curve from the stations, compare them, find some flares that are on both of them. So that should really be a real phenomenon happening. So that's where the fragmentation points are. And we can then build this kind of fragmentation history. We have the leading fragment, so the most massive one. That one is used for the dynamics fit. So we have, for example, speed in time. That's compared to the observation. And we have fragments, their masses, and their amount. And there is a resulting light curve here. It's maybe a little less visible because the colors are not so good, but yeah. And this is all well, but gross fragmentation can only account for like these small features on the light curve. If we want to affect the shape of the whole light curve, we would either have to use erosion model, so some continuous fragmentation, again, something that Tomáš talked about, but that would lead to narrower light curves. And that's not always the case that we want. So final approach that we use is differential ablation, which means that we are back to the single body simulations, but this time we don't expect the body to ablate uniformly. We expect, for simplicity, to have two components which ablate at their own rate, and therefore the resulting light curve is wider, and it can even have two peaks if the differences in their ablation rate or mass are big enough. So this approach in literature is usually modeled with a so-called dust bowl model, which means we have a small meteoroid, well mixed, and it heats up at the same time. Ablation starts also at the same time, but with different rates, which looks something like this. This is a pretty good model, but it has its limitations. First one is that the ablation rates or ablation coefficient have to be very, very different for a result to show like this clearly, because they have the same starting point. And also only small meteoroids can be modeled like this. And we wanted something that could be used on a wider variety of cases. So our idea was to make so-called avocado model. And that's because we have two layers, similar to how a real avocado looks. So they ablate one after another. And it could be basically done in any mix possible. So there could be a softer material on the outside and harder on the inside, like real avocado, or the other way around. The only downside to this that we have found so far is that we don't really know what kind of delay should be between those layers, or if they can overlap at all, because it's obvious that there should be some preheating of the inner layer, but we don't really have the physics of this. So right now it's just fitting to the model. So we focused on cases that were double peaked. We have 9 meteors of various shapes and also all kinds of parameters. We did some initial analysis with KB parameter that's used to estimate the type of meteoroid. And we have all kinds from asteroidal to cometary, except for the really weak one, but that's probably just because we have such a small sample. And also initial mass ranges from 0.1 to 30 grams. So obviously this isn't very suitable for the dust bowl model. So we were ready to try these out. But before that, we also noticed in some literature that the shapes of light curves were discussed. These are just examples. We have some that are really, really steep at the beginning, or some that are pretty smooth but have very deep decreases, and so on. And what the literature tells us about this, there were basically two ideas. One was that most of the curves should have a steep second peak. And this was an approach of Roberts and colleagues, who modeled it as two sequential releases of dust. So basically he used the dust bowl model, but this didn't really match our experience with these light curves. And the other approach was by Subasinghe and colleagues, and they noticed that yes, there were light curves that had a really sharp peak, and they usually belonged to asteroidal material, and the smooth ones belonged to cometary. This really didn't work in our samples. They were all over the place. It was basically 50-50, whether or not the smooth one was cometary or asteroidal. So for now, we really don't know if there is difference like this, or if our samples are just too little, and we will have to test further. So we also tested both dust ball and the avocado model where we could. So for the smallest ones, here they are. We can see, well, okay, this is single body, so we can see that this one really, really doesn't work at all. And we have light curves simulated from the dust ball model and from the avocado model. As we can see, the dust ball really is good for the ones that have bigger and sharper first peak, because that's the one that needs to ablate quickly. But for the ones that have shapes that are a little bit different, then the problem starts. Pretty surprising is that even in avocado model, the difference between the ablation coefficient had to be really big, and also the values were not very standard. In a usual meteors, they should be much smaller. So that seems to be a problem with the model somehow that we need to test later. And both models had problems with very sharp increases and decreases during the modeling, usually at the very beginning. And then if this was a very deep decrease, then either one wasn't too good. When it comes to fitting dynamics, they were all comparable. So we were basically just needing to focus on the light curve in this modeling. So our next idea was, let's combine the gross fragmentation and differential ablation. On one hand, we could make a more detailed model of the light curve. And what's more, when we simulate fragmentation, which in single body is basically hidden inside of the ablation coefficient, this could lower the ablation coefficient to more normal or standard values that can be found in the literature, since the differential ablation seems to make it much bigger than it should be. Also, when we use it with the avocado model, it could be a trigger for the ablation rate change. So we wouldn't have to worry about the delay I discussed before, because that would be the point where the ablation should start of the second layer, like this. So we could realistically overlay the ablation of the first and second layer, and that would definitely improve the variety of cases and light curves that we could match. Obviously, this required some simplifications. For example, we didn't really calculate anything about the shape that should be changed after the fragmentation. Everything in our simulation still stays spherical. And also, the fragments are only released from the first layer, so we don't have to mix the densities and the other parameters here. So we moved on to this kind of simulation. Five of our 9 double-peaked meteors showed some kind of fragmentation, but most of them were just small flares, usually some release of dust, and it didn't really seem like they would have too much impact on ablation. There was just one, and that's the most interesting that I'm going to show now, that seemed to have one big release of fragments that could correlate with the time where the ablation rate should change. So here we have it. This time the light curve is in, it's plotted over the altitude, so it's a little bit rotated, but that's okay, I hope. So we have once more single body. We can see that this doesn't really help at all, but it was a good first approximation. So we have some idea of what kind of parameters we should expect. So it seems to be a material that's not too strong, not too weak, and its ablation coefficient is in the expected range from the literature. So we moved on into the differential ablation, namely just the avocado model. And here we have two different materials, softer outside one and stronger core one. We see that the ablation coefficient are increased, and we can see that the fit of the light curve is better, but it should definitely be improved because there are some pretty steep places that it still doesn't reach. So then we moved on to the combined model. Here we have some changes in the density, but more importantly, there are very, very big changes in ablation coefficient. Interestingly, the second one is larger than the first one, but this could actually be because the first one is the layer that also fragments, and the second one we just let it be like it is. So this could also be hiding some maybe continuous fragmentation. And this one, as we can see overall, is improved again. And in this case, very interestingly, also the dynamics fit was much, much better. In the previous simulations that used either single body or just one of these processes, we usually had the mean root square about 100 meters. And here we could push it down to about 50. So that was good, but maybe it's just an accident in this one case. So we will see. And here is basically, we can see how the layers were ablating in the avocado model. And here they are in the combined fragmentation and avocado model. So we see the jumps, that's where the fragmentation points occurred. And this line is where we also started the second layer with the fragmentation. So it's maybe better seen when we also show the stations. We can see that there are some peaks. That's where the fragmentations happened. The stations weren't really in agreement with each other when it comes to the absolute brightness, but they show the same kind of fragmentations. Those were the ones that we were focusing on. And as we can see, it seems like the problems are once again with some decreases, which we still don't know what to do with, but the peaks seems to be very, very improved by this combined model. So to just sum it all up, we tried different approaches to our meteoroid modeling. We tested two different differential ablations model and concluded that the avocado models is more suitable for our cases. We also tested a combined fragmentation and different ablation model, which seems to improve our results. But we still have some weak points, namely the decreases in the light curves. We still don't really exactly know where the differential ablation should start, especially for the cases that don't show a correlation between fragmentation and ablation. So that is something to further test in more cases. And also we need to see whether or not we can find some correlation between the meteoroid type, material, and the shape, because literature suggests that it should be there, but we don't see it in our meteors so far. And that's all. So thank you for your attention.
Thank you very much, Maria. We have time for one question. Who was the first?
Thank you. Did you try simulate some fainter meteors?
Yes, usually these double peaked are basically fainter than the normal ones, because in the first part of my work I focused on bolides and their fragmentation, but there was not much to do with ablation, so we use these ones. But uh, if it's about overall faint ones, well, there is hard to find the double peaked ones that would be suitable for simulation, because they usually disappear in the middle where there is the decrease, and that's problematic then.
Okay, thank you.